Hello and welcome to lecture 15. We're going to continue the discussion on diodes and diode circuits. And in particular, the bulk of today, I'd like to start on this concept of rectification that we briefly talked about last time as one motivation for the need for elements like diodes, and then things that basically are related and build up on it, filtering and regulation. And this might take a little more than just today, but hopefully we'll make good progress today. So let's start with that same problem that we started as primary motivation last time. So I have a circuit like this, or rather, I have a voltage source like this. So we call this rectification. I have a voltage source. Let's call it input voltage. And this input voltage is an AC signal, let's say a sinusoidal function. So I'll draw it here. Let's say a cosine function like this, okay, as a function of time. So it has some peak value cosine of omega t, omega being the angular frequency. And that's 2 pi f. Omega is angular frequency. F is just frequency. Then this would be 1 full cycle. Let's say t. So the signal period t is just the inverse of frequency. Frequency is in hertz. T is time in seconds. Okay. Omega is radians per second. These are things that I think you've seen in physics again, right? Dealing with a basic sine function. Or in this case, cosine. Centered it at 0. Or I've put the peak at 0. So if I have a voltage like this, and I want to start from this and come up with something that gives me some non-zero average, because you see, like we said last time, the average of this is 0 over one cycle. But if I wanted something with a non-zero average, and ideally, ultimately, something with a constant voltage, so that I can go from, let's say, the wall plug to the output of what you have on your power adapter that you connect to your computer. We said for something like that, we would need to try to break the symmetry that we see between the negative and positive side. So one thought was to get rid of the negative side. And we talked about that briefly, so I want to build up on that. So imagine I want to start from this and deliver a voltage to some load. Here, a resistor, let's call it R. And I'm interested in the output voltage. Let's call this V. As a function of t, I cross this resistor. And this is how I've defined my polarity. Well, if I connect this directly, you will see that the voltage V in is directly appearing on the output. Let me call this V out. If I connect it directly, this is V out will just be V in. This is where the diode came into play. And we briefly looked at a situation like this. There I put a diode in there. And I think we talked about it, for instance, in the case where I had a capacitor connected here instead of a resistor. And we'll soon see the effect of the capacitor in more detail. But think about this circuit for a moment, what this circuit does. So imagine this is an ideal diode, and plot V out as a function of time. Okay? Think about it for a couple of minutes on your own. Maybe I'll give you a brief reminder that last time we talked in detail about the current voltage characteristics of a diode. And that looked something like this. So if you had a slightly positive voltage applied across it, if this is the diode, and this is V, and this is I. If you have a slightly positive voltage, and that would be a fraction of a volt, say about 0.5, 0.6 volts, then it would allow essentially any positive current. In the reverse direction, if you applied a negative voltage to it, it would allow a very, very small current. This current here, now I'm showing an exaggerated view, but that would be something of maybe, let's say, microamp or nanoamp or picoamp, depending on the diode. But so that's very small. And of course, if you increase that reverse voltage, eventually you will reach a breakdown, and it will allow the passage of current. And we'll talk about this region also in more detail later. But for now, we are concerned with the main part in the forward region. So very small voltage, but a large positive current, or essentially any positive current. And in the reverse, almost any, or within a range, any negative voltage, and a very small current. And we simplified this in several steps, but we said, you could even go as simple as something like this to represent its behavior approximately. Something that, without any positive voltage, would allow essentially any positive current, and it would allow no negative current regardless of how high a negative voltage you apply to it. Okay? So this blue line, or these blue characteristics, are what we called the characteristics of an ideal diode. And we looked at an example with that. So what I'm asking you here to do is to assume that that diode is ideal, take this input, this cosine input, and plot the output of the circuit, and the output being defined as the voltage across that resistor. Okay? So think about that for a couple of minutes. Well, so here's how to think about it. Take a couple of typical values of V in at different points in time, and see what the circuit is expected to behave like at those moments in time. Okay, so for instance, let's take this time t1 here. Let's take time t1. So the value of V in at that point would be its peak times cosine of omega t1. As we can see on that graph, that's a positive value. So at that moment in time, V in has a positive value. So imagine it's some, 3 volts. Well, if you wanted to solve this circuit for the diode, you have one of two possibilities. And we are, again, looking at it as an ideal diode. So we are not concerned with the whole exponential characteristics, but whether it's on or off. So there are two possibilities. Either the diode is on, which means there's no voltage drop across it, but it can allow any positive current, like the lines that I just drew on the characteristics that I just showed you. or it's off, which means it has a negative voltage across it, but there's no current going through, right? So if I have a positive Vin applied to it, so let's say, just to give an example, if I had 3 volts, in this circuit, and this is just a simple resistor. In the circuit, would the diode be on or off? Well, let's try. If the diode is on, okay, it looks like this, right? 0 volt drop across it, and it can allow any current in that direction. Also, you would simply, if you solve this circuit, you would simply get 3 volts divided by R, being that current. And that's indeed a current in the direction of the forward direction of the diode. What if I assume the diode was off? Then it would not allow the passage of any current. Okay, so the circuit would be like this. Now, what is the voltage drop across the diode? Imagine, there's still this diode here. I've removed it because I want to remind us that there is no current. But what is the voltage drop across the diode in this case? Sorry. What is V? 3 volts, right? Because there is no current, so there's no voltage drop across R. The entire 3 volts are appearing across the diode in the forward direction, right? Which is not consistent with the assumption that the diode is off. Okay? So this is a very, sort of the most basic diode circuit, if you want. And so with a simple analysis like that, we saw that if you applied a positive input to this, so if you were anywhere in this range of time, or in this range, where the input is positive, the diode would simply be on, conducting current in the forward direction, and not taking up any voltage drop, right? What does that mean for V out? It would just be the same as V in. So if you write your KVL here, minus V in plus VD, if you call this VD, minus V in plus VD plus V out equals 0. So to analyze this, I'm just doing my KVL minus V in plus VD plus V out equals 0. And so if V in is positive, like the example we looked at, we just saw how VD becomes 0 and V in becomes V out becomes equal to V in. So you can make an assumption that that's not the case, and you reach the contradiction that VD has to be forward, right? So I won't write it again, but if V in greater than 0, we can show that the diode is on. So VD is 0, and V out equals V in. On the other hand, if V in is less than 0, so the other half of the cycle, right here, then what happens? So imagine the input was minus 3 volts. So the diode is either on or off, right? let's assume it's on. So if my input is minus 3 volts, and the diode is on, which means there is a current going from left to right, I have a minus 3 volt rise here. I have 0 volts there. And then I have a current going down in the resistor, which means a positive voltage on the resistor. Well, the KVL is violated. Right? Imagine if Vin is a negative value, which means the voltage is really like this. If VD is 0, well, you can't have a negative voltage equal a positive voltage, right? So you will reach a contradiction there. And so you will conclude that the diode is off. And in fact, so there is no current, and the entire negative input drops across VD. So if Vin is less than 0, we can show that the diode is off. So the current I equals 0, and V out is 0. So this is actually the complete answer to this problem, because you will see that in the positive sides of the cycle, the output is the same as the input. In the negative sides of the cycle, the output is 0. So you've just thrown away that half. So if I were to plot that, so if this is my V in, this is V out. And this is it. This is a rectifier circuit. It has rectified the input and made sure that current goes only in one direction in the circuit. So the resistor sees only the positive half of the cycle. And so if you look at the output voltage now, it's quite asymmetric. And in fact, it does have a non-zero average. That's a DC component. So the output voltage has a positive average. You might say you have just built the crudest version of a DC power supply. So, you just put a diode in there and you give it an AC signal input, and you get something on the output that has a non-zero average, has a positive component. Now, not many of you might be willing to use something like this to charge a sensitive electronic device, like a cell phone or laptop, right? Because it's not a very, it's definitely not a constant output, right? So you want to do a little better than that. But this was the key part that we needed the diode for. Now, there's bigger circuits that you can make, and we will look at those a little later, that you might be uncomfortable with the idea of throwing away half of the signal. So you might say, can I somehow use that and flip that around? And you can do that. We'll look at circuits that do that. But for now, at least we have achieved the idea of creating a positive average at the output. I don't want to jump into the next step, but I want to make sure you guys take a moment and get a little comfortable with this. All we are saying is that in the positive half of the cycle, you have this flow of charge, as if there was nothing there. That's a switch that's open. That's closed. And in the negative half of the cycle, it's just like an open switch, like that. And it's disconnecting the flow of charge, and the output becomes immediately 0 because it's a resistor with nothing going through it. What I'd like to do next is, as you might imagine, is to try to stabilize this output a little more. This is really just swinging wildly between 0 and that peak value, Vp. We'd like to get something that's closer to a constant voltage. Okay? And for that, I'd like to remind you of the example we saw last time with a capacitor. Okay? So you might recall, in that case, we didn't have a resistor. We just put a capacitor in there. And we saw that during the first quarter of the rising, or during the rising part from 0 to Vp of the signal, the capacitor got charged. And so I want to see if I can use the charging of that capacitor. So to do that, I'll just add a capacitor to the circuit and see how it behaves. And what we are about to do, we call filtering. Now, why that's called filtering is a very serious topic. And you guys will take signals and systems at some point, and that will make a lot more sense. But I'll explain a little bit. Filtering, I'll hint at why we call it filtering later. But so here's the circuit. I have the same input, a sinusoidal signal as a function of time. And by the way, maybe I should, sometimes you will see a sinusoidal signal to be shown with a wiggly here like this. Okay. It doesn't really matter, because if I specify it like this, but if I say V of V in is a time-dependent function, it's the same thing. Okay. So I will have my diode here. And I have my resistor here. That's what I was trying to deliver this voltage to. But I'll just throw in a capacitor. So RC. I still define my V out in the same manner. And let's still assume that that's an ideal diode. So it's VD with an ideal diode. And we have the input voltage, same as before. And so this is V in. And it has a peak value. So I'd like you guys to take a moment and think about this on your own a bit. what does V out look like in this case? So all I've done is add a capacitor in parallel with that resistor. Let's imagine for a moment that we did not have the resistor this time. So think about the capacitor circuit only, what we discussed briefly last time. So think about the circuit that has only the capacitor, but the resistor has been taken out. What would the output look like then? If I did not have this R, if I took it out. So let's say I start here. V in goes up, and imagine the capacitor has no initial charge. So the capacitor has 0 initial voltage across it. As soon as you want to raise V in a little bit, you are forcing a positive voltage across the diode, right? And the diode immediately says, no, I'll do whatever it takes. I'll let any current go through, but I won't allow the voltage to go beyond 0. That's what you have on the IV characteristics. So what happens is, as soon as the input starts to rise, the diode will just turn on and allow the capacitor voltage to follow the input. So the capacitor voltage will keep going up with the input. At some point, the input reaches the peak value, Vp, and then it starts descending. Now, if you didn't have a diode there, if it was just a wire connected, well, the capacitor would keep following the input. That it would be directly connected to the input, right? So the capacitor would then start to discharge. It would send its charge back, so it would have a negative current, and it would discharge back into the input source. But because the diode does not allow that discharge, because the diode does not allow a current to go backward through it, that doesn't happen. So the capacitor just retains its charge. It stays at that voltage. So if you did not have the resistor, it would, let's say if you start here, the capacitor voltage would go there and then would stay there. And as the input goes down, the diode would just be reverse biased. It would have a negative voltage across it. There would be no current going through it. And the capacitor voltage would just stay there forever. And this is all if we did not have the resistor. There. Again, for a moment, we are saying that the resistor is not there, okay? So you're quite right. When the voltage drops, the capacitor would have wanted to do that if there was a connection here, right? Right? But the diode will not allow the charge to go through it in that direction. Okay? So that's what you would see. But now let's consider the full circuit where you have that R connected across the capacitor. Now what happens? Well, everyone was interested, or many were interested in seeing the capacitor discharge, right? Now it does discharge. So when the diode is on, so in that part of the cycle, when the diode is on and the input voltage is rising and the capacitor is just following that, because when the diode is on, it's just like a switch that is closed and the input is directly connected to the capacitor, then you have the same behavior when you start from 0 initial voltage. But then when the input reaches its peak and starts to descend, now the capacitor that would have liked to stay there at that voltage, like the blue line, well, now the capacitor has that voltage and it's connected across a resistor. You have an RC circuit, exactly like the kind of circuits that we analyzed several weeks ago. So you have the capacitor discharging in the resistor, actually. So it will start losing its charge to the resistor by setting up a current in the resistor. So there's that path. And so this is what happens. You initially have that rise, but then the capacitor will not retain its charge. It will start discharging. Maybe let me exaggerate this a bit. This is an RC discharge. So in that part of the cycle, the diode has become off because the input voltage has gone below the voltage across the capacitor. So the diode is off, but the capacitor does not retain its charge. It discharges into the resistor. And so this is what you get. Now, how long will this continue, this discharge? So there was a question, how come it discharges at a slower rate than it charged? It's a very good question. Any answer? So one important point is the rate of this discharge depends on the value of the resistor. You have the RC time constant. And so, depending on that, this could be faster or slower. But you're saying still fundamentally, why is that different from this, right? Why is that different from the way it charges? It shows a completely different behavior. I've drawn it much more slowly. It's not a sinusoidal signal anymore. The charging part and the discharging part are two different circuits. When you're charging, it's when the diode is on. You have a short circuit here. And the input voltage is directly implanted across the capacitor. So you don't see an RC discharge or charging there because both the resistor and the capacitor are connected to the same input directly. They don't interact. They each independently have the same voltage. And so you follow the input. Whereas in the other part of the cycle, the diode has become off. The input has been disconnected. Now you have an RC circuit. And you have an RC discharge there. And it's the behavior, and it's the value of R times C that determines how fast or slow that discharge is. So I have drawn something here that's relatively exaggerated. But let's go with this. How far should this go? How far should this discharge go? Up until this point, where it touches Vn. That's the point where the output, as it's going down, so you see the output is going down. The input is going back up again. They reach each other, and that's the point at which the diode voltage becomes 0 again. Beyond that, the input wants actually to go up, and the output, beyond that, this is what the output wanted to continue doing, right? But it doesn't do that anymore because as soon as the input reaches the same value and now it wants to go up, it will turn on the diode again. So this is what you will see. So after this, the input, the diode is on again. The output follows the input up until this point. And then again, you have the RC discharge. And this pattern keeps repeating itself. So this is V out in the presence of both C and R. And the decreasing part is just an RC circuit. Essentially an exponential decay. With the time constant RC. Now, this is a qualitative analysis, of course, but I'm relying, as I said before, on your having developed enough ease with circuits so that we can discuss these without going through every time writing KVLs and KCLs and so on. If you have difficulty following this, this would be a good time to actually go home and write the KVLs and KCLs for each of the cases that I'm discussing here and see if Vin is positive, how that leads to the diode being on, or if Vin is greater than, or it reaches that point where it wants to go above V out, how that leads to the diode being on. And all of these are in your KVLs and KCLs. Now, this is the behavior of the circuit. So now, and you know, we started literally from this point. But this circuit will never come back down to that point again. It will just go up and down between that VP and this lower value here. So you might say it's the variations between the top and bottom of the signal now have become less. It doesn't go all the way to 0 anymore, right? Now imagine you wanted to build a decent power supply where the variations are very, very little, right? So what value of capacitance would you choose? So, a big value. So if C is large, so imagine you have a given R, that's your load, that's whatever you're trying to deliver energy to. You want to increase the RC. So just give it a big C, and that will make these variations smaller. Incidentally, these variations are called, so this thing here is called the ripple voltage between here and here. That's the ripple voltage, the amount that the output drops during each cycle. And of course, for a good power supply, you want a small ripple. So a large capacitance. And what I'd like to do next is to actually calculate the value of the ripple current as a function of the parameters of the circuit. So that's my next exercise. What is the ripple voltage? Yeah, solve a system of equations. You have that exponentially dropping behavior as a function of time. And then you have this cosine function as a function of time. Solve them together to find the point in time when they intersect. And at that point, the value of the function will be known to you based on either curve. And so that's that value. Now you're an engineer. How would you calculate it as an engineer? Let's think about a good approximation. If this is going to be a good power supply, you want a small amount of ripple, right? You don't want a big drop. If this is, if the peak is 5 volts and the ripple is 4 volts, this is not really doing its job, right? It's a nice circuit question maybe, but it's not a power supply, right? So if the peak is 5 volts, I wouldn't want anything that has a ripple of more than, let's say, 0.5 volts, right? 10%, or even much less than that, okay? So I want a very small ripple, which means I want a very slow decay, right? Which means I want a large time constant. I want it to take a very long time to decay. So the time constant has to be large. RC has to be large. So let's try to calculate voltage for the approximate case when the decay is slow. So if VR is smaller, significantly smaller than VP, for which we need tau equals RC to be large. What does large mean? How large? Large enough, yes, yes. Yes, exactly. Now, what is my measure for enough in this case? So I want a smooth transition, but for that to happen, what should tau be greater than? It has to be greater than, significantly greater than the signal cycle. So during one cycle, it should not discharge much, right? So it should be large, or to be specific, to be much larger than T. So if we have this slow decay, and VR is significantly smaller than VP, then let's find an approximate expression for VR. So I'll draw the situation here that represents this slow decay. So now this is my output. Let me use a different color. And in fact, this has been going on for a long time, right? If my signal kept going, this has been going on. So if I have this situation where the ripple is very small, if this is V out, what we are saying is, in this case, between t equals 0 and that point in time, so let's call this T1. And we know that this is T. For T between 0 and T1, V out is what? It's just an exponential decay, starting by Vp and dropping with this time constant. By the way, I don't want to confuse things now, but it's something good to think about. Whether this formula is entirely accurate starting from that peak point. It's something I'd like you guys to think about on your own. But not now. It's, for when you get more comfortable with this. It's something good to think about. But for now, let's say this is just our RC drop, the way we've seen an RC circuit, starting with the peak value and dropping like that. And it drops very slowly. That's why it doesn't go down by much during that time. And this is basically my V peak. And this is how far down it has gone. So this point is Vp minus Vr. Okay, maybe I'll change these two also. Capital. Vp minus Vr. What is the value of Vr in this case? What is the voltage at that point? What is Vp minus Vr? It's the point that this exponential decay has reached at time t1, right? So Vp minus Vr is just V out at time t1, which is Vp e to the minus t1 over Rc. So here's where you put your engineering hat on. Would you leave it at this, or would you want me to do something else? Go one step further and simplify it. And any approximation that I can apply here? What is that time t1? So let's say if the cycle here is 20 milliseconds, how much would you expect t1 be if this decay is really slow? It would be 18 milliseconds, 19 milliseconds, right? It's just before you reach that point again, the next cycle. So t1 is very close to the big T, actually. So a first order approximation is simply to assume t1 is the full cycle. So actually, this is approximately equal to Vp e to the minus t over Rc. That's it. That's an expression for Vp minus Vr. So from that, you have Vr equals Vp times 1 minus e to the minus t over Rc. You have Vp, that's the amplitude of the input signal. You have t, that's the period of the signal. You have R and C, that's Vr. But that's approximate, because I assumed that the duration of the discharge is actually a full cycle. We know it's not, because t1 is a little bit less than t. But it's an approximation. Now, if you're a very maybe too serious an engineer, you will not be happy with this either. You say, no, I want to simplify it a little bit. One thing that people use a lot to approximate and simplify things is the Taylor expansion. You've seen the Taylor expansion? So do the Taylor expansion of this. What do you get? What is the exponential of x approximately if x is very small? What does the Taylor series tell you? It's approximately 1 plus x. So if indeed, as we have assumed, t is much smaller than Rc, right? Here, this assumption that I wrote there, Rc is much larger than t. Then, using that approximation, you get Vr approximately equal to Vp times 1 minus e to the some very, very small number. So that's 1 plus that small number, which happens to be minus 2 over Rc. There you go. That's an approximate expression for the ripple. And that's the kind of thing that you would use as a design rule, right? So if I have a problem and I want to, so let's say I have an input with a maximum amplitude of, with an amplitude of 10 volts with a period of 20 milliseconds, and I have a 1 kilo ohm resistor that I want to create a good DC signal for. Calculate the capacitor. Well, how much ripple can I tolerate? Let's say 10%. So Vr would be 0.1 Vp. And that tells you what T over RC is. If you know T and you know C, you know R, you get C. Okay? So let's take a short break. And this is hopefully also time for you guys to think a little more about this. What is the average of this signal at the output? I've kept saying, you know, we want some positive average. So what is the average of this output voltage? VP minus half of the ripple is the average. But now some people, I think, maybe said none of the above, and they're correct. Because this is approximate, right? This is an approximate value for that average. Been doing everything with approximations. This is not a linear drop. And even the value of ripple that we calculated was approximate. So this is approximately correct. Well, what is the average output current? So if I am interested in the current through the resistor, oh, this is by thinking in very simplified terms. I have a signal going between VP and VP minus VR, right? If this was a linear drop, the average would be the midpoint, right? So it would be VP minus half of VR. But that's very approximate, okay? So what is the average output current? Yeah, so it's just that. So I average is V out average divided by R, which you can work out on your own. Let me label these. So here's another question. At what point during the cycle is the diode current highest? Well, first of all, when is it that the diode current is, well, at what point during the cycle is the diode current negative? Never. Okay, good. Now, when is it that the diode is letting a lot of current through? That's when you're trying to charge the capacitor, right? At time t equals 0, if you calculate the just before t equals 0, that's when the capacitor was kind of reaching its maximum value, right? And was going to go flat before it realizes that it has to discharge in the resistor, right? But just before that, what's the slope of that curve, the cosine curve, as it reaches its peak? What's the slope? 0. So the capacitor current is reaching 0 at that point, right? Now, the resistor current throughout the cycle, again, thinking in the engineering approximation world, the resistor current is basically the output voltage divided by R. And it's more or less constant, right? It has some ripple, but it's more or less constant with that average value that we talked about. So if you're interested in the diode current, you know that the resistor current is more or less constant. When you want to, if you want to see when the diode current is very high, you have to see when the capacitor current is very high. At the point just before this peak, the capacitor current becomes 0, right? Because the dV by dt becomes 0. After that peak, the capacitor starts to discharge, of course, but most of that current is going, well, all of that discharge current is going through the resistor, actually, right? Not through the diode. Now, so during all this time, the diode is actually reverse biased. There is no current up until this point when the diode turns on again. Now look at the slope of the curve at this point, T1. That's when the charging of the capacitor starts, and that's when dV by dt of the capacitor is at its highest. The slope is at its highest. Look, here you have the highest slope, and that slope is what the current of the capacitor is as it's being charged by the input voltage through the diode. And gradually, it reaches its maximum, and the slope becomes 0. The capacitor current becomes 0 in the charging direction, and then it starts discharging in the resistor, and that's when the diode is off. So the diode current is actually at its peak at time t1. This is the answer. The diode current, so let's call it ID, is approximately IC plus I being the resistor current. So this is ID, and this is IC. I is approximately constant. IC is actually has the highest positive value at t equals t1. And so ID is highest at approximately t equals t1. So now I want you guys to calculate that t1, or let's look at maybe this, just the difference between t1 and t. Let me call this delta t. That's the duration of time when the diode is on. It's charging the capacitor. For the rest of the cycle, it's off. The capacitor is just discharging. So delta t is what you call the diode conduction interval, the interval during which the diode is conducting. What is delta t? Maybe let me mark this here. what is the diode conduction interval? Can you try to do that on your own for a couple of minutes? So I'm interested in finding that delta t, the difference between this big T and T1. That's the time during which the diode is on, it's conducting. Yeah, so look at the curve there. It's this time that I'm interested in, right, between these 2 points. Well, here's one way to look at it. This is part of that cosine curve, right? You can look at it here or in any of the cycles, right? So it's the time that it takes this cosine curve to go from this value to that value. The time that it takes the cosine curve to go from this point to that point. Now, this point is VP minus VR in terms of voltage. This point is VP. So all you're looking at is the difference on the time axis for the cosine curve, right? So the graph VP cosine of omega delta t has to have reached the value VP minus VR. Okay. Now we know that this omega delta t is a small fraction, a small portion of that cycle, right? So cosine of a small number. What does the Taylor series say for the cosine of a small number? If omega delta t is very small, cosine of omega delta t is approximately 1 minus, this is the Taylor expansion. Go do it. See, 1 minus half of omega delta t squared. So cosine of x, x being small, is 1 minus half of x squared, approximately. Right? So this will give you a good approximate expression. So Vp times 1 minus half omega delta t squared has to be Vp minus Vr. So then you have omega delta t being approximately the square root of 2 Vr by Vp. Correct? And so you have these, right? So this is so delta t then will be approximately, so omega is 2 pi over t, and Vr is what you have from before, t over Rc Vp, which then you can simplify and verify that I've done this correctly. So that's an expression for the conduction interval, diode conduction interval. That's the part of the cycle during which the diode is on, is charging the capacitor up. So if you have this, then if you have this, you have that point T1 that we were talking about. T1 is just 1 delta T before the end of the cycle. So you can put that in the equation for the capacitor voltage, which is just that cosine, and calculate the value at that point. You will get the diode, the maximum diode current during the cycle. Now again, these formulas are approximate, but they are very good for designing something. So you can specify characteristics that you want for a DC power supply, how much ripple you can tolerate. Why do we care, for instance, about this maximum current in the diode? That doesn't really affect my output voltage, does it? It could blow up the diode, right, if it can't handle it, right? Or think about it in another way, it will not allow the capacitor to charge at the rate that we want if the diode cannot handle the maximum current that it needs to. Okay? So this is something that you have to take into account. And the maximum that a diode can tolerate, you'll find from the data sheet. Now I want to say a few words about why we call this filtering. What have I filtered? I have filtered out the negative part, you might say, but we call that rectification, right? So we already gave that a name. What have I filtered here? Initially, my signal was this. Right? Now I have come to something like this. Something that, you know, I'm not drawing very accurately, but something like that. Right? You might say, let me try to represent this very approximately. Can I say this thing that I've gotten now approximately is this? Maybe it's a straight line plus some wiggles. Right? So it's a straight line maybe plus something like this. I'm not drawing this very well, maybe. Right? Or actually, to be maybe a little more accurate, I should say something like this. If I add these two, I get something like that output that I had. Almost a straight line with some ripples. Right? What I have done, what I have effectively filtered, is I had this signal. This signal has just a single frequency in it. And I first rectified it, so I got rid of this half. So I ended up with only this. Right? That was the rectification. Now that signal, you might say, has some average value plus some large variations. Right? You can think of it as having two components. One average constant value plus something that has a lot of variation. Right? I have turned that into something that does have the average plus very small variations. I have filtered out most of the variations. I have the component that was varying with time, I have gotten rid of a big part of it. You know, every time you tune into a radio station, for instance, right, or any communications channel, you're tuning into some frequency. What you're doing is you're putting a filter there and throwing away all the electromagnetic waves with all the different frequencies that are all around us at all times, and just keeping the ones with the components that you want. And in the filter, you will have resistors and capacitors, maybe inductors. This is a very simple example of that. I have thrown away most of that frequency and kept, in this case, I was interested in the zero frequency or DC value. I've kept that. So I've filtered things out. This is what you would call a low-pass filter. It has allowed the passage of the very low frequencies, meaning, in this case, the zero frequency, the DC signal, and has limited greatly the passage of higher frequency components. What would the optical equivalent of this be when you filter some frequencies out? Sunglasses, right? You're hoping, for instance, in many cases, to get rid of the ultraviolet, right? To have UV protection. Or anytime you look through colored glass, that's an optical example. So, and a very, very wide range of phenomena are thought of and analyzed in this manner. And so when you read about Fourier transform and decomposing a signal into its various frequencies and signals and systems, I hope you will be able to make connections to many more things than just a voltage in time, just a telecom application. And you will quite possibly encounter many examples of trying to apply a filter when you're doing a software project. For instance, if you apply a filter to an image, let's say you have an image and you're trying to get rid of noise. You might apply a filter, meaning you're trying to get rid of a lot of the high frequency variations because you know that that's just adding noise to your image. And you will keep components that are not spatially varying too much because you know that, let's say, your image doesn't have features that change every pixel, right? So this is very, very broad. And this is just one example of that. So this is why it's called filtering. And of course, it's not our topic. We don't have time to go into this in depth. But I hope it makes a connection for you. So we'll leave it at that for today and pick it up next time. Thank you.